Welcome everyone. We'll continue our discussion from the last lecture and work towards development of a framework in which we can analyze evolution or coexistence of multiple genotypes in an environment. And this particular field of analysis is called evolutionary game theory. So, just to recap from where we had finished last time, in a two species environment where two distinct genotypes are coexisting, our dynamical equation which captured the dynamics associated with frequency of one particular genotype can be represented as dxa by dt is equal to xa times 1 minus xa times f of a as a function of x minus f of b as a function of x, where the vector x is just the composition of the population in the environment at that particular instant. So, when we are talking of two particular genotypes, the vector x will comprise of xa component, which represents the frequency of individuals belonging to genotype A, and xb, which is frequency of individuals belonging to genotype B, and xp we also know that xa plus xb is equal to 1 at all times. So, essentially the vector x is just one variable xa and 1 minus xa, because of, and that's true because of this linear relationship that we know exists between xa and xb. And then we had talked about the steady states associated with this system, and the steady states are xa equal to 0, xa equal to 1, which corresponds to no a and all b, and all a and no b, and any particular composition of the population such that fa of x is equal to fb of x, which implies any such composition where fitness of A is equal to fitness of B would also constitute as a steady state associated with the system. So, then there are different relationships that can exist between Fa and Fb, and if I am looking at Xa going from 0 to 1 and on the y axis have Fa minus Fb, then we discussed a couple of cases. In case number 1, Fa minus Fb was always greater than 0 for all values of x, and this implied that in the environment it was all A. And in the other case that we did, Fa minus Fb was always less than 0 irrespective of what composition of the population we worked at. Fa minus Fb was always less than 0, and this corresponds to a situation where any non-zero composition associated with the two genotypes moves to a situation where there is all B and no A. So, this particular condition ensures that the system moves in this direction towards Xa equal to 0, and Fa minus Fb greater than 0 ensures that system moves in this direction towards Xa equal to 1, which is all A, and this moves in this direction, which is all B. So, we did these two compositions, but then we recognize that there could be other scenarios such that we are not commenting yet on the structure of these functions. We do not know what kind of functions these are these linear or non-linear functions. So, there could be compositions which are defined by this vector x such that Fa of x is equal to Fb of x. Now, let us imagine that one of those structures, again we are not commenting yet on the mathematical nature of Fa and Fb of x, but what we will assume sort of is, should Fa and Fb curve intersect the x axis at any given composition, any given non-zero and non-1 value of Xa, what would the nature of the steady states associated with that situation look like? So, for example, if we take a case like this, again our x axis represents Xa, it goes from 0 to 1, and y axis is Fa minus Fb. Each of these, remember, is a function of Xa on the x axis. And now if the graph associated with this looks something like this, maybe that's what the graph looks like. So now we want to comment on what's the fate of this system given that the dynamics is defined by dxa by dt equals xa times 1 minus xa times fa of x minus fb of x. So, we know the form associated with the first two terms, but this third one we are not comment on the mathematical framework which defines this, but let us say this term looks like this as x is varied. So, what's clearly evident here that there exists a certain x naught below which when the composition of the population is such that the A type individuals are less than x naught, then Fa minus Fb is greater than 0, which means in this section of the graph individuals A are fitter than individuals B, and vice versa, that in this composition of the population where Xa varies from x naught to 1, it is Fb which is more than Fa, and hence Fa minus Fb is less than 0. So, what happens in a scenario such as this, and that can be easily seen from the analysis that we have been doing so far, that let us look at. So, first thing to recognize is that there are 3 steady states: xa equals 0 because this term is 0, xa equals 1 because this term is 0, and xa equals x naught because at that value of x naught this term is equal to 0. And we want to comment on the stability associated with each of these three terms. So, again we follow the standard procedure. Let us to study the first one. Let us introduce a disturbance such that xa is equal to 0 plus delta, which means bring the value of x to this point, and at this point x is a small value delta which is positive. Now, if delta is positive, that means this quantity is positive. Since delta is small, 1 minus xa is always positive unless xa is equal to 1, but we know that xa is much smaller than 1 in this case, which is just equal to delta. And for this particular composition of the population, Fa minus Fb is at this value which is greater than 0. So, all of these are greater than 0 for xa greater than 0, hence dxa by dt is greater than 0 at x equal to delta, which means with increasing time xa increases and we move in this direction, which is away from the steady state that we started with, hence this particular point is unstable. Similarly, we can look at the next steady state, which is xa equal to 1, and the disturbance that we introduce now is xa equal to 1 minus delta, which means we bring the system to somewhere here which is 1 minus delta. Now, starting from this point, we look that at xa equal to 1 minus delta, xa is positive, 1 minus xa is always positive unless xa equals to 1, but xa is not equal to 1, xa is 1 minus delta. So, this is positive, and at this particular point Fa minus Fb can be seen is negative here, which means dxa by dt is less than 0 because it is a product of 2 positive and 1 negative numbers. Dxa by dt is less than 0, and hence starting from this point the system moves in this direction. Hence, this point is also unstable. So, xa equal to 0 and xa equal to 1 are both unstable points. Okay. While it is also evident from these graphs that any deviation in this region moves the system in this particular direction, any deviation from this point in this direction moves the system towards x naught. So, we can see that deviations from either side bring the system towards x naught, then hence intuition implies that x naught should be a steady state, stable steady state associated with the system, but let us just go and actually explicitly check for stability of x equal to x naught. And if we do that, we will introduce deviations from x equal to x naught on either side and track which way does the system move once it is disturbed from its steady state x equal to x naught. So let's introduce a first deviation where x is equal to x naught minus delta. If that's the case, that means this is the x that I am talking about, x naught minus delta, and at x naught minus delta x a is positive, 1 minus x a is positive, and f a minus f b at this point is also positive. So, all three factors are positive, which implies dx a by dt at x naught minus delta is greater than 0, which means system moves in this direction towards the point that it was disturbed from. Similarly, if the disturbance that is introduced here is x equals x naught plus delta, which means now I am talking of a disturbance which is here, this is x naught plus delta. At x naught plus delta, x a is positive, 1 minus x a is positive, and f a minus f b in this case happens to be less than 0. And if it is less than 0, it means the system moves in this direction again towards the point that it started from, towards the steady state that we are talking about here, which is x equal to x naught. Hence, at this point dx a by dt is less than 0, and you get a case where you have this particular point x equal to x naught as a stable steady state. So, of the three steady states that we have in system, x a equal to 0, x a equal to 1 and x a equal to x naught, two of the steady states are unstable, and the one which accounts for non-zero frequencies associated with both genotypes is actually the stable steady state, and hence this type of a system which would exhibit f a minus f b such as like we just described is actually said to be a representative of a case where there is stable coexistence of multiple genotypes. Because the only steady state which is associated with the system actually ensures that both genotypes coexist in the environment and not one of them is eliminated, like what happened in the previous two cases that we discussed. And the case that we had started this discussion last time around when we started talking of evolutionary game theory, of the case where there is a cheater, there is a mutant bacteria, a cheater in the population which does not commit cellular resources towards production of an enzyme which is responsible for breakdown of a polymer that the bacteria are then going to use for energy, is a case which is represented by this sort of a framework where there is a stable population, because we saw that if the mutant population goes down very small, then the mutant is actually more fit than the parent genotype. But if the mutant is everywhere and there are only a few parent genotype individuals left in the population, in that case mutant's fitness is less than the parent. Hence, somewhere in between these two extremes there lies a particular frequency of the mutant genotype such that the fitness associated with both the genotypes exactly meet each other, and that is the stable steady state that we are looking at in an analysis such as this. Alright, so that is stable coexistence. There is one more case regarding this that we want to talk about, and let me sketch that out first. Again, so x axis is x a, which goes from 0 to 1, and y axis is f a minus f b, and now my graph looks something like this. So, it starts with a negative value, which means that f a is less fit, f a is less than f b, that means a is less fit as compared to b at this particular population composition. However, if there are mostly a's in the population, because this region here represents high values of x a, that means there are lots of a's and very few b's. In a scenario such as that, it is f a which is more than f b, and hence f b minus f b is a positive. And in between there is one particular point where the fitnesses of the two genotypes exactly match each other. So, again we do a similar analysis, we know that our steady states are going to be x a equals 0, x a equals 1 and x a equals x naught. So, again let's first let me write down the equation once more. These are both functions of x like we have been talking about so far, and this is the relationship that's given graphically here. So, if you look at x a equal to 0, we disturb the system, bring it to x a equals 0 plus delta. Again we are only introducing the positive deviation, the negative deviation does not really make any sense for us. So, this is delta, and at this point x a is positive, 1 minus x a is positive, but f a minus f b at this point is less than 0. Hence, as the system moves forward in time, the composition of the population moves in this direction towards the point that it was deviated from. This implies dxa by dt is less than 0, and hence this particular point in this case is stable. What you should note at this point is that what we have just shown, by changing the nature of f a minus f b graph, the point x a equal to 0 has basically switched its stability. In the case that we just finished, x a equal to 0 was an unstable steady state, but in this case x a equal to 0 represents a stable steady state associated with the system. All right. So, this one's done. Let us talk about x a equal to 1. So, again we disturb the system and bring it to a state 1 minus delta, which is somewhere over here. And at this point, at this particular point, x a is greater than 0, 1 minus x a is greater than 0, and f a minus f b is greater than 0, which means system moves in this direction. Again towards the point that we disturb the system from, towards x a equal to 1, hence this point is also stable. And okay, this dxa by dt is greater than 0. And our last intermediate point, which is again we will disturb it two ways, but intuition here or this analysis of the other two steady states associated with the system sort of suggest that x naught should be an unstable steady state, because the systems want to move away from that system, because the system wants to move away from this particular steady state. So, x naught, if we deviate it x naught to x naught minus delta, which is somewhere over here, then again at this point dxa by dt is equal to positive times negative, which means a negative number, which is what is here. Dxa by dt is negative, hence the system moves in this direction away from the steady state that we are talking about, x naught. Similarly, x naught plus delta, this particular location, implies dxa by dt is positive times a positive number, hence greater than 0, and that means the system moves in this particular direction away from the steady state that we started with, which confirms that x equal to x a equal to x naught is an unstable steady state. So, the difference between this case and the previous one is just that the steady states associated with the system have switched stabilities now. The points which were unstable in the previous analysis have become stable and vice versa. So, what is this? A system like this is actually called, so the previous one was called coexistence of the two species, because the stable steady states corresponded to a situation where both the genotypes had a non-zero frequency associated with them. Here, the stable steady states are those which are associated with one of the genotypes going extinct and one of them taking over the population. However, depending on where you start your system from, that's the determining factor as to which particular genotype goes extinct and which particular survives. For instance, if we look at this point x naught, if we see here, and any disturbance brings the system to x naught minus delta. If the system is existing at x equal to x naught and any disturbance brings the system to x naught minus delta, what will happen is that the dynamics of the system will ensure that the system moves in this direction towards x a equal to 0, which means towards all b. However, if that initial fluctuation or disturbance to the system was such that it moves it to x naught plus delta, then from here the system prefers to move in this particular direction towards x a equal to 1, which is all a. So, in a scenario like this, what is happening is that the initial disturbance, if the system is existing at x a equal to x naught, it is the initial disturbance which decides which direction does the system move to, and that particular disturbance which could be a random fluctuation that happens in the environment decides the fate of the two species which are involved. So, the starting point of an analysis such as this is the key determining factor which decides what happens to the genotypes, and hence this type of a framework is called a bistable system. Because this system exhibits two stable steady states, and which one you land up on is decided by where you start your system from. So, if you are operating at x equal to x naught, your starting point is decided by which way does the disturbance that enter the system push the system, and from there on the dynamics of the system take over and take you to one stable steady state or not. All right. So, these are 4 scenarios associated with this type of an analysis, and just to summarize, it could give you 4 different type of results, all A, all B, coexistence of the two, or a bistable system. In theory, you could also have more complex forms of these relationships. For instance, it is not inconceivable that you might have x a looking something like this. So, if your graph looks something like this, now you have lots of stable steady states. Now you have lots of steady states associated with the system. X a equal to 0 and 1 always exist, and in addition you have these 4 intermediate states. And what you should show is that in a scenario such as this represents a stable steady state, this is an unstable, this is a stable steady state, this is an unstable steady state. So, this if f a minus f b exhibited a form such as this, then what you are talking about is coexistence, but coexistence could also happen 2 different ways in this system, and again that is decided by what was your starting point. If the starting point of the system which had an f a minus f b defined like this was, let us say this point is x a equal to x naught. If the starting point of the system was between x a equal to 0 and x a equal to x naught, then the coexistence happens at this particular steady state, let us call this x a 1. Whereas, if the starting point was between x a equal to 0 and x a equal to 1, then the system is going to converge to this stable steady state, which also ensures coexistence, but at x a equal to x a 2. So, again these systems can exhibit different dynamics depending upon the precise nature of f a minus f b curve. So, the next question that we have for us is that how do we actually arrive at analytical natures, analytical expressions for this f a minus f b expressions that we might have. And in order to do that, we need to understand something called a payoff matrix, which comes from a game theory, which comes from the field of game theory. And the way we are going to look at is in a microbial context, think of it like this. So, we want to define what is called a payoff matrix. And before in the context of before we talk in the context of microbial populations, let's talk in terms of game theory. Let's imagine that you have a two-player game, and the strategies which are available to two players are called strategy A and strategy B. Okay. These are the two strategies that are available to the two players. And the payoff matrix is defined as the following. You have strategy A and B competing against strategy A and B. And the way it's defined is that if strategy A, so if you are playing, so let's say this is your strategy, and the columns represent opponent's strategy. And the way you define this is, this elements of this payoff matrix define what is your payoff, how much do you stand to gain or lose if you were playing the row strategy and the opponent was playing the column strategy. For instance, if you are playing A and the opponent was also playing with strategy A, your payoff would be small a. On the other hand, if you were playing strategy A and the opponent was playing strategy B, your payoff would be small b. If you were playing strategy B and opponent was playing strategy A, then your payoff would be C, and if both of you were playing strategy B, then your payoff would be D. So, again what is important to note is that elements of this matrix represent returns for row. So, these are the strategies whose elements are being represented here. Which means the returns that you are going to get when you play this game. So, if you are playing with strategy B, opponent is playing with strategy C, this C return represents your return when you are playing B and opponent is playing A. It does not talk about what does the opponent get when it is playing with A. Okay. Alright, so this is what is called a payoff matrix, and in the next lecture onwards we will start to use this framework of a payoff matrix from game theory to incorporate a scenario where microbial populations, which we will treat as two players here, can be analyzed in a framework which is very similar to this payoff matrix from game theory. Thank you.